Let's get started. So, first thing, let's talk about reading quizzes. You know, in reading the feedback you guys gave, there were some comments about the reading quizzes being out of sequence with the class at this point. I've been trying to do that, but I lost track, and you were right. And there were also some comments about the time that it takes to do those reading quizzes, which is actually a fear of mine. I don't want them to take you more than 15 minutes. Right? My goal is for them to be 15 minutes or less. And so to immediately address those, I deleted all the unopened ones, plus the one DJ did early, and moved the one that was for Friday, because there should have been one due on Friday. I moved it to do 26th. Next Friday. And so that's the last of those. I did, you know, on the thing you guys put in, the vast majority of people said that they are putting in 4 to 6 hours per week of study, which is, was it 4 to 6? Yeah, I think it was 4 to 6, or it was somewhere around 6 was the average based on the numbers people put in, which is what is considered the target for college classes. So I felt a little relieved on that, because, you know, if somebody knows I had over 10 on there, if people were answering over 10, then I'd feel hugely guilty, right? Because you only have so much time. Thank you for answering those questions. I will try to use those to make further changes in future years. I don't think there's much more that actually could have been done this year based on your comments, but I can use them for future years. Okay, second thing. How did things go on Friday? I mean, what were your impressions? How did it feel? What did you learn?
I liked it, but low-key, I feel like I should have been in the biology section, just because I felt like everything was just
the vernacular. I don't know if it was because it was aeronautic material and stuff, which I'm not as familiar with. Yeah. But like, they start the presentation, I'm like, I'm doing the I'm just like,
you're doing the what now?
And I just found it kind of funny, because I think on the last one, she talked more about like a more bio life in space type thing.
Yeah.
And the people in the room apparently aren't as familiar with that.
Right.
And so they were sympathizing with that, but I was just like, that's how I feel about all presentations.
Yeah, that's the one I understood the best. It's like
Very humbling.
Very humbling. I was sitting next to Chad during the first talk I was at, and it was exactly, well, it wasn't exactly the same, but it was the same area that I did my PhD research on. So I'm like, yeah, because I had to tell Chad, hey, this is what I did my research on. So that was cool for me. But that's one of the things when you go to a conference, usually they're much more focused. You have this meeting is only on this small topic. And the people going to those meetings are people who understand that small topic. Because otherwise, yeah, it flies over your head. And so yeah, I heard comments from the people who rode with me about, well, I feel dumb now, you know, or ignorant. Not dumb because it's not a sign of intelligence or anything. Was it profitable?
It was. Because we're going to be doing that soon.
Hopefully.
A more dumbed down version.
Dumbed down version. No, you guys would be just as smart.
The posters made sense, though. So there was like a 3D printing figures. That makes sense.
I really liked the posters. They were nice.
Good. Did you guys get to the, when did you guys go? You're the only three that I didn't see there.
We were in the morning aeronautics and space B presentation, like at 10 something, in Ackley.
Okay. So that would be right after I went upstairs to the third floor. Because I was in the aeronautics A until the poster session at 9 to 10 or whatever. Then I went upstairs after that. But yeah, so I saw those. You remember to turn in your sheet and your name badges. This is just so we have evidence that you came, that you paid some attention and didn't just, you know, go la 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 la. Yes, DJ.
I left my folder with that stuff in my dorm room. Can I run out?
Yeah, sure.
So
I turned it on Doodle. You want it, the physical too?
No, that's okay if you're on. Do you like scan your badge or something? Or?
Yeah, I scanned it.
I mean, I want the badges as evidence of being there.
I have it with me.
I have had people who didn't attend. This time, really not much of a concern because, like I said, I saw all the three of you there.
So I think I have my badge in the room, but if not, I took a picture.
Okay.
Okay.
I'm not sitting here trying to find ways to take away points.
It's like you saw me.
Okay. The posters, hopefully, that helps you in getting your poster done. Is everybody started on their poster? Please all say yes.
Yes.
Okay.
Do you want that by Tuesday?
I would like that by tomorrow, yes, because I need to get it printed, and they said to give them a week to get them printed.
What's the time frame on Tuesday? Tuesday night, Tuesday.
Let's say, yeah, I'm probably actually I'll call them today, but I'm probably going to try to drive over there Wednesday afternoon. I'm hoping that's enough time. Right, get them there Wednesday and then pick them up Monday is my hope. But, saying Tuesday just to make sure, I'll call them after class. And everybody, you saw the template on Moodle for making your poster, right? Okay, so want to make sure that's out there because I haven't talked about the template, I don't think, and I just made it 8 by 10. All right, let's review for the exam. First thing, a couple students noticed already this morning, it's not chapters 28 through 31 or chapter even 28 through 30. The test is only going to be over chapters 28 and 29. Why only 28 and 29? Well, as was noted by students on the class thing we did, things have kind of bogged down in the last couple of weeks. All this stuff is so interesting and different and weird that we've kind of slowed down. And so we're only going to have the 2 exams on the test. And there's not that much here. Now, let me tell you, if you can do the one problem in its entirety that I made on the chapter 28 review, you should be set. Because it uses everything that we learn in relativity. Starting with, it doesn't start with the postulates of relativity. You do need to know those separately from that one problem. The postulates of relativity, that the speed of light, I'm not sure which one's first and which one's second. I'm not going to ask you which one's the first one and which one's the second one. So which one's the first one?
Laws.
Okay, so the first one is the laws of physics are the same in all inertial reference frames. Well, we've got to define an inertial reference frame, a reference frame in which Newton's first law, the law of inertia, works, which means that fundamentally, inertial reference frame is not accelerating. So the first postulate is that the laws of physics work exactly the same in any non-accelerating reference frame. The second postulate is the speed of light in vacuum is the same in all reference frames. All of relativity is built on just those 2 postulates. Well, all of special relativity, which is all we've done. On those 2 postulates. And we have time dilation equation, length contraction. You need to identify which reference frame has the proper time and which has the proper length. So proper time is the time measured in a reference frame where the clock is stationary with respect to the events you're measuring. So if the events are 1 heartbeat and the second heartbeat, the proper time is going to be a clock that is stationary with respect to my heart.
So what about those problems where the ships are moving at different speeds and stuff?
Well, let me just talk briefly about the big problem. It's a big. How many people have looked at the worksheet for chapter 28?
Just a little bit.
That's a big, hairy problem, right? And in the problem, you have a rocket, or I changed words. I re-uploaded it to fix the wording incongruities. This call is spaceship. A spaceship, it's the USS Enterprise, right? I told you that I gave you mass of the USS Enterprise in theory. So the USS Enterprise leaves the Earth and travels at 0.866 C for 20 years as measured by Earth. Now, who measures the proper time for this trip? The spaceship. Because the spaceship was stationary both at the beginning and the end. Everything was just right there. So the spaceship measures the proper time, which means the 20 years is a dilated time. So how do I find the proper time then? I'm just going to assume Andrew said it right. Okay, so now that we have that confirmed, our relationship is delta t is equal to gamma delta t 0, where delta t 0 is the proper time. and gamma is equal to 1 over the square root of 1 minus v squared over c squared. So if we want to find delta t 0, then we just solve that for delta t 0 by dividing both sides by gamma, which is exactly what you said, right, Andrew?
That's right.
All right. So we can find the proper time that it takes for the ship to make this trip. Now that speed 0.866 is made so gamma is roughly 2. So if it takes 20 years as measured by Earth, the proper time is 10 years. Then it shoots a missile back toward the Earth at 0.95 C with respect to the spacecraft. What measures the proper time for the missile going to the Earth? The missile does. Not the spacecraft, not the Earth, but the missile. So then I'm going to have to do some translations from one reference frame to another. The way I laid out for you to solve that is to first use the velocity addition equation to find the speed of the missile with respect to Earth. Because the Earth has the nice fixed length it's traveling, the proper length. So we haven't even talked about proper length. The proper length is determined by the reference frame where the starting and ending points are stationary. And so the Earth measures the proper length. And so I know what the distance is it has to travel. If I find the speed in the Earth reference frame, I can easily find the time for the Earth. And then I can convert from that time to the proper time. And from the proper time, then I can calculate what the time will be for the spacecraft. Right? So I can't just go directly from Earth's time to the spacecraft's time because neither one's the proper time. I have to make a stop in the middle of the proper time. That's using a lot of relativity, but then there's more. But wait, there's more. Be able to apply, okay, we all of these we've already talked about, but we still have this. Be able to work with relativistic momentum and energy. And so I included the relativistic momentum and energy calculations in that problem. Now I tell you, you can use either the Earth reference frame or the rocket or spacecraft reference frame. Use the spacecraft reference frame. It's actually a little bit easier because the initial momentum for the missile and spacecraft are both 0 in its own reference frame. But I gave you those so you have experience using, with the practice problem, those. And I will, hopefully this afternoon, have the time to record and upload so you can all study it before tomorrow. I say hopefully. I've got to file my income tax and I've got to get that done. Those are 2 musts that have to be done today. Yeah, it's a struggle. Okay, so that's chapter 28. That's our relativity. What kind of relativity did we study? Special relativity, which means it's the simple one. It's the one that doesn't involve accelerations or the effects of mass. So general relativity is a lot harder. That's why we only did special. When I was your age, when we talked about relativity in our physics class and the teacher kept talking about special relativity, I was like, why are we doing the hard stuff? Why don't we just do the general stuff first, right? Because don't you think of general physics as the easy physics and something else is the hard? Yeah, that's not the way it is. And yes, okay, probably wrong to say general physics is easy, but it's easier. A lot of people complain about, what? That's not a freshman level class. It's not the same as a freshman level history class probably. But if you compare it to a junior or senior level physics class, and Chad here could give you some insights, this is simpler. I don't want the class to be hard, but there are realities. Chapter 29, the particle nature of light. So we did the photoelectric effect experiment to see for ourselves, taste and see, that light was behaving as a particle and not as a wave. But the week before that in lab, we had done 2 experiments that said light behaves as a wave. Diffraction and polarization. So we had diffraction and polarization and interference. There's a difference in diffraction and interference. Diffraction is bending around a corner. Interference is 2 waves interacting with each other. I have always used the two to being the same thing just because you have a diffraction grating and then the light interferes. And so I think of them as the same, but technically they're different things. But those are things that could only be explained by a wave nature. But then we have the photoelectric effect that could only be explained by a particle nature. Likewise, the Compton scattering. Compton scattering, you had a change in frequency for photons that were scattered. Can't happen with a wave. Could only happen if it's a particle. For a particle, it has momentum. The momentum for a particle is equal to Planck's constant over the wavelength. And so if it has momentum, if it loses momentum, its wavelength is going to change, and thus, if it stays in the same medium, its frequency changes. So we could explain Compton scattering, a change in the wavelength, a change in the frequency of the same medium, by a particle theory, but not by a wave theory. And then we have X-rays. For X-rays, it was the characteristic spectrum that was showing a particle behavior in pair production. Pair production we did not talk about. So you don't have to know anything about pair production, but I will say very simply what pair production is. Pair production, I have a photon, it's cruising along. The photon hits something like a proton, and all of a sudden the light disappears, but its energy has to go somewhere. Its energy goes into making two particles. So an example of pair production is making a positron and an electron, particle and its own antiparticle. So it's a process where you convert energy into mass. So that's another thing that could only occur if you have a particle nature. So make sure that you understand these things and you can do calculations. For Compton scattering, we had that simple equation that was the shift in wavelength is equal to that. So you should be able to calculate what the shift in wavelength is based on the scattering angle. And you need to know that that's calculated. We didn't do the derivation, but that's calculated by using conservation momentum, relativistically, and conservation of energy. And then for X-rays, you should be able to calculate, equals HF, the formula that actually Planck came up with to calculate what the energy is for a given frequency in the characteristic X-rays. And the photoelectric effect, you need to know the whole shebang. Here's my surface. I have light comes in. That light comes in and it hits a little electron that was hanging out here. The electron gains energy. And then the energy that it gained makes it go like this. And so I have energy in equals HF. We have kinetic energy out. And for energy balance, the energy in is equal to the kinetic energy out plus the work function. The work function is the energy required to take the electron away from the metal. If the work function was 0, the electrons would just escape from metals, right? But they don't just escape, so that means it requires energy to take them off. And that's what the work function is. And so we did this in class. Energy in was HF. And so we solved this for kinetic energy out. And that's what we graphed in our lab report. Now I put here kinetic energy out. It's actually the maximum is what we were working with, because those electrons could always have bounced off things and lost additional energy. And so the maximum is going to be where it didn't lose energy. That's what we worked with. So make sure you understand that process and can deal with that. You can calculate, for instance, if a photon comes in with this frequency, then an electron comes off with this energy, the work function must be by that equation you can calculate. That's that's not much, but that's the stuff that's going to be tested on. So any questions? I mean, hopefully I didn't miss anything. Any questions about what's going to be tested on?
So since we're only going over 2 chapters, the synthesis is going to be one on each and then one on one other one?
The synthesis, I will try to have at least one on each, but there will almost certainly be 2 on 28 and 1 on 29. Because 3. Because we had a whole lot more calculation in chapter 28. Any other questions?
Is there going to be a calculus section?
Because we're just getting through the quantum mechanics, I have my quantum mechanics calculus question on the final exam. So, no. Mira.
This is just pertaining to like our grade as a whole. Are you going to be doing the grade calculator?
Yeah, of course.
Okay.
Andrew.
Will there be MCAT questions on it as well?
I'll do like I did last time with extra credit. On the evaluations, there were some people who definitely did not appreciate having those MCAT questions there. There were some who did. So that's kind of a mixed bag. You know, I know we can't please everyone, but I'm trying to. Okay. Moving on to material that will be covered on the final exam. Early quantum models, we've gone through the plum pudding model. We've gone through the planetary model. We've gone through the Bohr model. I'm going to review a little of the Bohr model, and then we'll talk about the quantum model. So the Bohr model, remember, Bohr had 4 assumptions. The first one is the electrons orbit the nucleus in circular orbits. The second one, that they have only specific, quote, stationary orbits with discrete energy, so they can't give off radiation. Hence, they won't collapse in as physics says they should. Still uncomfortable with that myself. Number 3, that when electrons jump up or down from one stationary state to another, they're going to either absorb or emit a photon with energy equal to that gap. So the energy of a photon is HF. So if it goes from here to here, it's going to give off a photon with energy HF equal to EU minus EL. That's E up minus E low. If it goes from here to here, it's going to have to do that by absorbing a photon with exactly that same energy. So that's his third assumption. And then the final assumption is that the angular momentum was quantized. And based on this and using classical physics with those assumptions, he was able to calculate that you have the radius in the ground state is this 52.92 picometers. What does pico mean? 10 to the minus 12. The size of the nucleus is measured in femtometers. What does femto mean? Negative 15. So that first talk that most of us saw at the conference, he was using a femtosecond laser. A laser that's pulses are so short they're measured in femtoseconds, which that is different from what I did. I was using an ultraviolet laser with like 20 nanosecond, I think, pulses. Those are short pulses, but not nearly short. Ultraviolet is going to interact with the material fundamentally different than he was using, was it microwave or infrared? Yeah, so they're gonna interact fundamentally different. The ultraviolet is going to break bonds directly. The infrared is going to heat it up. So but if you're doing such a short pulse, you don't have much heat. So anyway, so you have then the radius, the other radii that are allowed are n squared over z. What is z? I'm not sure if I even defined that. Well, no, I did. Z is the number of protons in the nucleus. This equation works for all hydrogen-like atoms, atoms that have only one electron. So I'm going to do a problem in a minute that has a helium singly ionized. So it has one electron, that's hydrogen-like, and it'll work. Energies. The energy levels are likewise E1 z squared over n squared, where E1 is equal to 13.6 minus 13.6 electron volts. So there's only specific energy levels available. And so using, I think it was the third hypothesis, then if I look at the energies for electron going from one state to another, so for instance, this one here, that's going from, it has marked minus 3.4 electron volts. 3.4 just comes by putting a 2 in there. 2 squared is 4. 13.6 divided by 4 is apparently 3.4. And so I can get what this energy is. So how big is that energy? Just looking at the picture.
Would this be the difference between negative 13.6 and negative 54?
Yep. So it's
10.2.
Oops, put the parentheses the wrong place. I have to put it here. So there's a 10.2 electron volt drop, and so that 10.2 electron volts is going into a photon. So I have F is equal to 10.2 EV over H. I want to do this another way. Here's the way I want to do it. This is all correct, but it's easier to do it like this. Remember we had that, so it's a lot easier to just say, well, that's equal to 1240 nanometers times electron volt over 10.2 electron volt. That's roughly equal to 120 nanometers. And then once I have the wavelength, I can calculate the frequency. Yeah. Oh, yeah, that's the question. So you can see this 120 nanometers. What part of what part of the electromagnetic spectrum is 120 nanometers? What range is visible? Okay, 400 nanometers to 750 nanometers. This is shorter than 400, so that makes it ultraviolet. Because if we'd done it frequency, it would have been on the high side. It's based on frequency. So this is an ultraviolet photon, and that's the lowest energy photon you can get if it's falling to n equals 1. All the rest of them are going to be higher energy, so they're more ultraviolet, harder, we say. So these Lyman ones are all ultraviolet. We can't see those with the naked eye. These Balmer ones, if you look at this, that's going from minus 1.5 to 3.4. That's 1.9? 1.9 electron volts. If you do the same calculation, 1240 nanometers divided by roughly 2, that's about 620 nanometers. What color is that? That's actually red. But yeah, I'm close. Green's Jason. So that's a red photon. So this one here is red. And then if we go to higher energy, we're going toward blue. And so those Balmer ones are visible. That's why they were found first. We can explain that spectrum using the Bohr model. And of course, the Paschen one here, that energy from 0.85 to 1.5, that's going to be 0.65. And that's going to turn out to be infrared. And so these are all infrared and beyond. You're going to do a problem. A singly ionized helium atom, that is 4,2 helium plus, has its electron go from n equals 4 to n equals 1. What is the, quote, spectroscopic notation? Do you remember that? The notation for the characteristic peaks. Now we're not using capital S with things on them. We're using the shells. What letters of the alphabet do we use for the shells? Not orbitals, but shells.
Is it like an order? Like
It is in order.
like G H.
Is it
That's not right.
Hey,
Go with
Oh.
26 options.
KLMN, capital letters, we use those to indicate shells. So the K shell is the n equals 1 shell. And because this is ending in 1, that means it's a K. Yes.
Does that have any relation to the SPDF?
No.
None at all.
No, but we'll get to that in today's lecture if time should last so far.
I think
So this is going to be a K, and then remember we used a Greek letter. What did the Greek letter stand for? Alpha, beta, gamma, delta. What do they mean?
1, 2, 3, 4. Those are just numbers in Greek.
Yep. So how many did it change going from 4 to 1? 3. So it's going to be a K what? Yep. So it's going to be a K gamma characteristic, if you will, the way we did the X-rays. Then what's the wavelength of the emitted photon according to the Bohr model? Wow. Based on what we just did, I'm going to have delta E is equal to E1 times Z squared over N1 squared. Actually, and put N1 squared, that was right. I'm going to put a 0 instead of a 1. So there I put in numbers. 13.6 times Z was 2, so times 2 squared is 4. So it's going to be 3 times 13.6, right? We have 2 negative signs to make it a positive sign. So 3 times 13.6 would be 40.8. 3 times 13 is 39. Yeah. So 40.8 electron volts, and then finally, lambda is equal to 1240 nanometers times EV over 40.8 EV. So that one I can't do in my head, which is kind of silly because if it was 1240 divided by 40, I could do it. Yes, Trace was in the ballpark there. So it's 30.4 nanometers. This was for a helium emission going from n equals 4 to n equals 1. Now, I ripped right through that, right? Kind of had some advantages. I knew what I was doing. I prepared the problem beforehand. Any questions before I throw an identical problem with different numbers to you?
Okay, where did you get the 2 that you squared?
Okay, where did I get the 2? The number of protons in the nucleus was right. It's the number of protons in the nucleus there, and it's squared. So for helium, there were 2 protons in the nucleus, hence 2 squared. Question?
So the numbers right there on the bottom with just the N, The 4
These-
minus 1. Yeah.
Yes. So this was, I screwed up. Squared. Can't forget the squares. Mm-hmm. So that would be let's see. (64/16). That turns out to be harder for me. So that's going to be yeah. I hate it when I make mistakes, but I prefer to be corrected, as we've all learned by now. It's positive. So 13.6 times 60 divided by 16 is 51. Okay, so 24.3 nanometers. I'm glad you asked the question.
So it is just the ends.
Yes.
Yeah.
Okay, now let's go to your turn. So as your table, an ionized carbon atom. So this is the number of things in the nucleus is 12, the number of protons is 6. A +5 charge, which means it has only a single electron remaining, so it's hydrogen-like, and we can use what we learned. Has its electron go from n equals 3 to n equals 2? What is the spectroscopic notation this time? And what's the wavelength of the emitted photon according to the Bohr model?
So it's pretty much the same, just different numbers. Okay.
Oh, that's not good. Let's try again.
Which one shows you the electron volts? Which one shows you the electron volts?
What do you mean by which one?
Did the last problem give us electron volts? I'm talking about this.
That. Here's
There you go. There we go.
So is negative 13.6 a constant? This has just been stable most of these.
Is what?
The negative 13.6, is that a constant?
It's calculated from. I took it out. It's calculated from this work here, but I took out the variables that give you that number.
So, but yeah. So we just use negative 13.6 for that.
Yeah, for easier, just use my 13.6 electron volts. Yes.
No, because if you add protons to it, it's no longer carbon.
Oh. Yeah.
Oh, wait, you're right.
Yeah. All the things you want to do.
That's good. All that by the difference.
I changed it from 1 to 0.
I think,
Yay! She's gonna cause some problems. A little bit. Like hopefully you read it because we don't know that. Alright.
Oh, two.
that makes sense. Two.
So So this paper here.
I'd actually put that down. That's not what I have.
Yes.
I'm
Maybe I'll start writing that. That's one, two, and then we'll do
Well,
the next.
yeah, that's a separate thing. So what is this?
That's because the inverse of a difference is not the same as. Oh, that's where you're at.
Here, but then I think I forgot to change something here. I'm wondering why he put the 4s up here. Is it because he wanted to do common denominators?
It's because there was 2 squares and he just multiplied it answer there.
Oh, so like that.
Yes, that's what I was just
That's where the 4 went.
distributing.
I was like, what the heck?
Well, with the calculator, you don't have to do that.
Let me see.
Alright.
I should watch it.
Yeah.
Why didn't I watch that for your book?
It's
Oh, because we're looking for the wave.
it's the one that ends up.
Wait, what do you mean with the calculator? You want to do that?
Well, I'm saying, do you want to multiply things within your equation with each other, or do you want to just multiply the whole equation once?
Because alpha's
Like, do you want to multiply once or twice?
Once!
Okay,
My life easier.
that's the thing.
I think it's.
Would I say we're on?
Sure you do. Okay. It looks like most people figured out what's our answer. 18.2 nanometers. And what is the notation for it? Okay. So it looks like we got that, right? It won't be on the test tomorrow, but on the final, if we have something like that, we can do it, right?
Right.
And this would be a synthesis because it took multiple steps. One more thing about the Bohr model. If you take de Broglie's hypothesis, remember de Broglie said that a particle like an electron should behave as a wave with the wavelength is equal to h over momentum. If you take that and you say, okay, I want to set up a standing wave for an electron doing circular orbits. That's the same calculation as the whole goblet. You know, you tap a goblet and it rings. It rings because it's resonating, and the resonance you're hearing is the n equals, actually the n equals 1 resonance. But that means you have one wavelength going around it. And so what he found was, well, something we find in physics. If you have integer number of wavelengths is the circumference, then your wave can resonate. And it turns out that the radii you get with integer numbers of the de Broglie wavelength for the circumference exactly match what Bohr found from his work. So de Broglie is saying the wavelength is equal to h over p, and that we have resonance for the electrons orbiting the nucleus, gives the exact same outcome as Bohr's quantum hypothesis did. They're both quantized because you have that resonance. There's only certain wavelengths that will resonate. Whereas Bohr said my angular momentum is quantized. So both of them agree, and both of them are wrong. Now, the calculation we just did, that calculation is pretty solid. You can talk to Chad. He's writing a paper right now about the things that make what we did not perfect. But it's pretty solid, like I said. But there are some problems. So here's successes for the Bohr model, and then we'll talk about some failures. So it maintained agreement with the previous results. That is that an atom is mostly empty space with a nucleus at the center that's positive. And it predicted energy levels, and it gave a reason for the electrons not to collapse into the nucleus. Those are all good successes. But just like with the Rutherford's planetary model that people instantly realize, okay, it's better, but it ain't right. People looked at the Bohr model and they said, it's better, but it's not right. And one of the things that was wrong was that it turns out if you have an electron going from a 3s to a 2p, oh, what's that? What's a p? Well, those are the L's. And if it does that, you get two different lines instead of one. What we've been doing is just going from 3 to 2. This is what we just did with the carbon atom, right? We went from 3 to 2. And we got only one answer. But it turns out that there's more than one answer in real life. There's two. And the Bohr model doesn't allow you to have two. It only allows you to have one. So that was a sign that there is a problem. So this is called fine structure, the structure in that pattern that is a little more unique. Furthermore, as we understand things now, we can't figure out where the electrons are. We can't. We can figure out where they're likely to be. We have no idea what path they travel. So the idea that the electrons are doing circular orbits, we chuck that into the recycle bin. It's simply not what is believed anymore. It was nice with the Bohr model. It makes it easy to understand. But now we say we have no idea where the electron is. We can only tell you that it has a higher probability of being here and a lower probability of being there. And that's really what gave birth to one of the two derivations of quantum mechanics, is that we don't know where the electron is. What can we find? So here's a picture that shows what we call an s orbital. The s orbital is not a sphere. The s orbital is a fuzzy thing. The darker it is, the more likely we are to find the electron there. The hazier it is, the less likely. Electron could be all the way out here for all we know. It's just not very likely. So the quantum model, we don't have a shape for the path the electron orbits. We don't. You know, some people think, oh, P, it's orbiting in a dumbbell shape. No. We don't know what it's doing. We just know that's where it's most likely to be found, is in that dumbbell shape. Here's the actual, somebody was asking, the equation for what E0 is. There is what E0 is right there. In the Bohr model, N told you everything. Chad could tell you, N doesn't tell us everything. We spent a lot of time finding rules for two additional quantum numbers. And those additional quantum numbers tell us different things. So now N, which we named the principal quantum number, its job is to tell us the energies. So principal quantum number tells us the energies of the electrons, primarily. But then we have additional quantum numbers. Now remember Bohr, Niels Bohr said L equaled NH bar. The angular momentum was some integer multiple of h bar, or h over 2 pi. That we take as completely incorrect. Instead, the angular momentum is square root of L times L plus 1 times h bar. Still has a fundamental unit of h bar, but this here is not n. These L's, told you we'd get there, the L's are telling us about the total angular momentum. That's what this quantum number tells us. And it also tells us about the shape, the geometry of the orbital. And so L is called the orbital quantum number. And we have the rules that L has to be an integer, can be 0 up to 1 less than n. And that rule comes mathematically. It comes from the actual derivation quantum mechanics. It's, you know, people ask, where do these come from? It came from doing the math. So it's just an outcome of nature. Then we have our third quantum number, m sub L. M is the magnetic quantum number, and it can have values from minus L to plus L that are integers. And it tells us about the orientation of the angular momentum. So if I have an atom with L equals 1, it has an angular momentum of square root of 1 times 2 is the square root of 2 h bar, 1.4 h bar. What orientation is it? Could be anything. The L sub z tells me the orientation. But the thing that's really weird is, if L is equal, or L sub z, the M sub L. The M sub L tells me the L sub z. The L sub z, the angular momentum in some arbitrarily selected z-axis, is going to be 1, 0, or minus 1 h bar. My total angular momentum is 1.4 h bar, but in my arbitrary axis, it can be h bar, 0, or minus h bar. So it can't be lined up with my arbitrary axis. Bizarre, right? I mean, why can't the angular momentum have the direction I'm checking? But quantum physics says it can't. And so if you put these together, you have, well, there's one more quantum number, spin. I just don't have time to talk about spin, so I will pick up with spin after the test.